Pointers. Well, pointers in the C programming language, you are not ready for them. Yeah, but despite the fact that this video here before has not much to do with pointers, for some programming beginners, they are a sustainable source of confusion when facing them for the first time. Nevertheless, I will talk you through pointers in under 30 minutes, at least I will try. Welcome to myCTalkthroughs. So, pointers is a topic, and as I claim in the title of this video, I'm going to reveal everything you always wanted to know about pointers in the C programming language, but were afraid to ask. For that, I need to incite myself, and when I say incite, I mean you. Wubba Lubba Dub Dub, here we go. There are 5 big questions to answer in the C about pointers in the C programming language, and these 5 questions are essential. So, what are pointers and why they exist at all? What are pointers used for? What have pointers to do with strings? What is pointer arithmetics and what is that good for? And eventually, what else is going on with pointers? So, the latter one is basically a useless example, more or less useless example, but it is hard to wrap your head around. So it is an approach to demonstrate that if it comes to pointers, at least once it's worth to put the whole head into the rabbit hole. And after getting answers to these 5 questions here, you should be ready to be released into the wild of pointers and survive for a respectable while. So, question number 1 is, what are pointers and why there is a need for them? First of all, don't panic. Pointers itself in C are not that complicated to understand. The hard part is pointer arithmetic, but later more about that. The idea and the need of pointers within your computer come with your memory. Well, not your memory, but the one of your computer. Imagine your computer's memory like mailboxes, but not like this ones here. Imagine it more like PO boxes. PO boxes you can rent and let your mail be sent there. These boxes are usually available in some store or post office. You can have them in different sizes, but usually they are numbered and arranged in sequential order. And of course you can store information in such boxes like letters. You see, such PO boxes have a lot in common with the RAM in your computer. Unfortunately, renting a lot of PO boxes somehow exceeded my budget for this video. Here comes the cheapskate version with modest means I had at disposal. Matchboxes, which serve in an analog to RAM. And to identify space in memory, I have just numbered them with hexadecimal numbers. No rocket science so far. That is pretty much the same how your RAM is organized. And now let's say we have some values you want your computer to remember, like these numbers here. You check the available size and put it somewhere. Better to say your computer puts it somewhere. For example, here we store some numeric values. But if you want to store some type which does not fit in, you cannot store it in these boxes. Values of type letter are simply too big here. To store our value X, you need a bigger chunk of memory. Here, from hex 0A to hex 0B is enough space to store our X. That's nice, but in some way our data is some lost now, and the spot where we wanted to store it in the first place is still empty. And here comes this, the trick. Instead of storing the whole data at hex 03, we prepare us a pointer. The pointer is a value of type pointer to a letter and is nothing else but the address in memory where X is stored, not the data itself. From the value of the pointer, you now know where to find it. From the underlying type information, you know the size of the value you are looking for. So if you now want to pass the value X around, you just need to handle over the pointer to find the value. You just check the pointer value and see that our letter X is stored at hex 08. Here you can get it out and even manipulate it in place. So that whole thing is called by reference. Well, how does that look expressed in code? So in our little example here, my value will be of type integer, and I will name it with an identifier X and assign the value 23 to it. That has already something, but not much in common with pointers. Pointers are the agreement that you can not only store the value in some box, you can also store that number where you stored some value in some box. So now I will prepare some pointer, and that pointer shall be also of type integer, but it's not type integer purely, but it is a pointer to an integer. And it is good practice, but not necessarily needed, that you name that in some way to make clear that this is a pointer and not some kind of ordinary value. And to that pointer, I can now assign the value to where I stored X. And to make that clear, I use the ampersand sign. So this line here means nothing else but I declare a pointer to an int with an identifier pointer underline X, and I already assign the value where X is stored to that pointer. The asterisk here belongs to the type, not to the identifier of the value. It indicates that we are creating not an integer value, but what we create something pointing to an integer value. So the pointer variable is doing what the name of the type suggests. It points somewhere where an integer is stored. In some way, it is like a name card with an address on it. And that asterisk is reused in the case we want to use that name card to find an address. So what I can do now is I can declare an Z, and to that Z I can now I can find that pointer value again. So in this case, I'm also using the asterisk, and I use pointer underline X, but here I will not get the address where X is stored. In this case, when no pointer is around, the asterisk here, sorry, not when no pointer is around, when no type is around, the asterisk here will give me back nothing else but the value which is stored at that point. So the meaning here changes to something called dereferencing the value. One could say to the integer with identifier z, assign the value which is stored at the point where pointer underline x points to. So now we want at least to have a quick look at what is here stored at all at the moment. And for that, I put in here this. And as you see, at that point here, I will print out y. So we have no y, or? So what I really want to put here is, of course, z, and size of z. So what should be shown now is the z value. So dereferencing the value where the pointer points to. So eventually it should end up with a 23. And the size of z, which should be the size of an integer. We have a look. And really, it gets us a 23 and a size of 4 bytes. So, what is if we want to put out or print out the value of the pointer? What is that now? We also do that. And here you see it becomes some negative, very big negative number, because here we say we want to interpret it as an integer. Now we want to interpret it as an hexadecimal number. And here that is nothing else but the address where the value is stored. So here we have now 23, which is equivalent to the value which is stored under the identifier x, and the size of the z, where we it's the same like any other integer. And after that we see here the address where pointer x is stored. Yeah, the example leads us directly to question number 2. What are pointers good for? Yeah, one thing they are good for has also to do with your memory. Memory, you can roughly differ between the so-called stack and the heap. Greatly simplified, the stack is used by any instruction your computer executes to work from, and due to its proper order, it is very fast to work from the stack and on the stack. But the stack has also disadvantages, and one is that you need to know at compile time what you want to put there to make use of the access speed. Also, the size on the stack is limited, and if you want to allocate memory dynamically, and in C as a programmer, you are fully responsible for both allocating and freeing memory, you quickly come into trouble. But there's a solution for that, and that is the heap. I like to imagine that as a heap of boxes, and that boxes are also numbered, but what you are looking for when allocating memory is a chunk of sequential ordered boxes which are all empty and large enough to place your values in. And if you have such a red line leading you from box to box, the only thing you need to know is where you want to start writing your values and that you can use a pointer. That is a big use case already, dynamic memory allocation and organization. But the by far more essential justification for the existence of pointers is the mutation of values out of scope. For example, in a function, here it is about the actual function as, here it is about the actual function as pointers. What I really want to express is that the main function of a pointer is to change the value in memory and directly to access it there. I will show you in a small example. I'll start here with the small example from before, and I just delete these 2 lines that it gets some more, that we get a better overview of what is going on. Let's say we want to change the value of x within some function. First of all, we need to declare a function in C that I do up here, and that is I want to alter the value of the integer x. And to do so, I will put the function itself here. So I have now here better I put here an A to make more clear it is something different. So this is only the function signature, and here is the function itself. What I will handle over here is I want to handle over the value x itself. So before I create some pointer or anything, I want to change the value of x within some subfunction. And for that, I will call alter the value with x as an argument. In here it will be handled over as an integer a. I will raise a by 1, print it out to make sure it is really higher now, and then right after calling the I will also show x here. For the moment, we abandon here everything with pointers just by commenting it out. So what happens if I run this code? As you can see, I get here a 24. That is a 24 outputted here. But if I later output it, after returning from the function alter the value, you can see it is still a 23. And that is exactly the problem what pointers can solve. This x here only and really only lives within the function main. If I handle the value over into alter the value, it is really a copy what I handle over. It is not the value itself. I do not really handle over x and then I can alter it. No, I only make a copy of the value, change the value by adding 1, output it, and latest when this curly brackets here appear, it disappears. It disappears in nothing. And that's a problem we will address now. We will alter the value by a call by reference. And to show you the difference, I just put it in here. I create a second, some different kind of a sub procedure here. but this time it goes directly, it handles over a pointer to an integer. So what I handle over here is an address, what I want to do within this function. And now we have a look at the function itself. So I have a pointer to an address. I name that pointer B. Here I look at the value which is stored at the address pointer B holds, and to that value I add 1. Then I print it out like I also did here, but this time I do not print out the pointer. Of course, I again print out the value of where the pointer points at. And here, just to check, I will check the address of the pointer. Afterwards, I check the size of the pointer just to, just because. And here I do something. I will add, I will decrease the pointer B just to show you that this is not what we want to do. Maybe we postpone that sometime because it is maybe too confusing. So what is going to do here? What is going to happen here? Now, if we call that function and also we call it with the x value, we cannot use x itself. We have to use the address where x is stored, where the value is stored. We are not really interested in the exact address. What we handle over is look into the box where x is stored, and there you can do something with x. And this is not depending on the scope where x exists or not, because we handle only over the information where x resides. So what happens if we execute this? So as you see, we have a value of 24, and that value is still 24, and afterwards it stays 24. So far, so good. What you have seen now is that with pointers you can directly manipulate the spot where a value stands. That's a very efficient and very fast way to change a value. But I have to confess that you can do by far more things with pointers. Especially system programmers juggle pointers like artists at the fun fair. And there is another way for a very obvious application for pointers, and that is what I will show you right now. Yeah, question number 3 is, what have pointers to do with strings? To answer the question, I have to start with some bad news for you. Strings are not a distinct type in the C programming language. So what is a string then? In C, a string is defined as an array of characters which is terminated by a specific control character. So, for example, hello world is in reality of your computer's memory an array of HELLO, comma, space, W, and so on, and eventually with a \0. So \0 does not mean 2 characters in C. The preceding / only indicates that the following character, in this case the 0, shall not be interpreted as a value, but as end of the string. This is called an escaped characters. So let's have a look at an example. Here I have just to print out some hello world, but instead of just printing it out, I define it here new as a character, and as a type of character, as an array of characters, and I assign already a value, in this case hello world. And if I do not mention any kind of number here, then automatically during the initialization, here the \0 will be added but not be visible. That leaves me with 12 characters which I can print out in this string. The most simple way to do so is printf %s and then the value x. So let's do that. What happens here? The screen shows me hello world as expected. Under the hood, of course, I can also access only a single element of the array. For example, here with %c, only at the index 0, so the first character should be an h. We will have a look what happens if I execute that, and really I have the h here. So from that point of view, of course, I can now access every single character with a simple loop. So I can access every character within this array of characters by looping over the string from 0 to under 12, so 12 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I don't want to show you here the \0, but if I execute that, you see hello world appears put into the single elements of the array. So if a string is nothing else but an array of characters, then we can, if we want to pass around a string, or if we want to use a string value, then we can also access it in a way that we create us a character, a pointer to a character value. We name that in this case pointer _x, and assign to it the value where x is stored. So instead of passing around the whole value h, e, l, l, o and so on, we only pass around the value where we want to store the first character. And we don't give it a length or something, we just say or have to keep in mind that our string is over if it comes to a \0. But the \0 is not visible here, because if I output a string, then the C programming language automatically knows, the printf function knows that is not the part of the string I want to output. So here I have now a pointer, and that pointer says nothing else but point to the place where my string, my character array is stored. So where the first character is stored, where it begins. And here I do nothing else, but I want to output now exactly that value. So what will be outputted here is an address. so far it is only a point in the in my computer's memory where that value is stored. If I want to access the value itself, I have to dereference that pointer value. In this case, I do that with the asterisk here. If I put an asterisk before the pointer x and tell printf whatever this value here is, interpreted that as a character, then it understands if it is a character, then it can also be an array of characters. In this case, it will be a string. So what happens if I output this now? As you see, it outputs H only. So it only understands here is the beginning of this string. It only outputs a single character because under the hood, this pointer here points only to the H and not to the complete string. It is on us as developers, as programmers, now to go on. And that leads us directly to pointer arithmetic. So here comes the answer to the question number 4. What is pointer arithmetic? We know already that it is possible to pass a pointer value only instead of passing all the values stored around. So we spare all that copying, finding new space, reserving new memory, storing the data, manipulation of the data, copying the data again, freeing the memory, passing the data to the desired spot, and so on. With that capability, you can now create arbitrary chunks of memory, and you can create lists, which single parts you can easily access directly, as long you know the width of the single involved data types. And with that, you can then create so-called linked lists, which you can quickly search in for or iterate over. And you can link structures even forward, backward, and create so-called double linked lists and so forth. And for all that, you can use pointer arithmetic. I promised you before to explain that to you, and I redeem this promise with a simple example of iterating over a string. But don't worry, I just used our example from before here. I hope you remember that we left here with a pointer, and that pointer holds an address where the value of x is stored. And if we dereference that pointer with the asterisk here, then we can also read or write exactly to that spot and read that value at that spot. So, what if we do not use dereferencing, but if we use that pointer and we raise it by 1? What will happen then? Pointer underline x plus plus means that the pointer will move to the right. In reality, it moves to the left, but that let us not be confused by some details now. So if we use this here, pointer x or pointer underline x plus plus, then we are moving forward and move the pointer forward in memory. So the pointer does not point to that spot in memory, and we don't, it does not point there anymore. It points 1 unit, and the unit is defined by the width of the data type forward. So if you add something to the pointer with plus plus or with plus and then a value, then you do not assign a new value to the memory at that spot. You skip forward a few units with your pointer. And with that ability, you can even go out of scope by plus and minus. And that is pointer arithmetic. So let's have a look here at our example and just print out the pointer here after we moved it. What we expect to will happen. Before, our pointer point at age. If we raise it, the pointer value by 1, where will it point then? We have a look, and as you see, the pointer now points to the spot where the E is stored. So if we now make the full step here and we have also a look at what does that mean to the address? The address before was pointing to exactly the spot where X is stored. Where does it point now? So again, we run the whole thing. And as you see, the address here is exactly 1 unit higher. What is the unit? The unit is a byte. So now it is 1 byte higher. It moved some, and at that spot the E is stored. So our string is nothing else but a representation of values which are stored in a row, and that we are going through now. And if we want to go through, we do nothing else but raising our pointer by 1. You have to be a little bit careful. We raised our pointer now by 1. So we moved to the E. If we now move even more, we can also use this here. We can also use pointer plus 10. So our pointer is in the beginning as at the age, pointing at the age. Then we raise it by 1, it's pointing to the E. Then we raise it by 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after that, it is pointing to the D. Let's check that out. And really, as you see, it is here pointing to the D now, which we output. So what happens if we raise it again by 1? If we just do that again. So I execute that, and here you cannot see it because there is not really standing some value, some useful value, at least not. Here is just a value which cannot be interpreted as anything which is of value which could be a character. But we can go on with that and even try to leave our complete string here. It is possible to do so, and we do that. And here you see, now we left even the \0 area, and here is some value which is completely arbitrary. We don't even know what stands there. Maybe it's garbage, maybe it's some useful thing. And just make sure that in the end we will return here, we can also go back. And if we go 2 times back, we will land at the D again. So our pointer is really pointing around in the memory of your computer. So if you shrug your shoulders now, let me tell you, this is awesome. Due to the fact you don't need to read or write anything when moving pointers is really, really fast. You can, if you manage pointers, you can nearly access anything in low to no time in your computer. And that makes pointers a very mighty tool and essential for system programming and time critical applications. But this power comes with a drawback. Using pointers helps for fast execution times, but you really need not only to organize your memory from the beginning, claim it, initialize it, use it, and free it later. If you handle the access with pointers, you need to know every little piece of your memory, and pointer arithmetics comes with no limits and no security nets. If you run out of scope with your pointers, you easily create a mess. In best case, your application will just not work. In worst case, you access memory of your system, other applications, or even create bad damage in running processes. And even before Peter Parker, you should know that you should be aware of the saying, with great power comes great responsibility. So pointers are a mightful and mighty tool, but you have to use them with care and knowledge. Yeah, all that makes the last question here. What else one can do with pointers? Besides all that Joaquin Phoenix Joker-like destructive tendencies which come to mind now, with pointers you can do all kinds of crazy stuff. They are a gift and they are a curse. But more, they are a gift. To do the real tough stuff, you need to be a by far better coder than I am one. So I stick here to something kind of easy, but stunning example to show you how the pointers work as pointers to specific types to access chunks of your memory in an unusual way. That is because pointers are nothing else but variables to addresses, and a pointer is always related to a distinct type, which informs your program how far to read and write data from the spot your pointer points to. So here comes an example which includes all kinds of weird usage of pointers, types, values, pointer arithmetic. Yeah, and for that I will change our little example here some by doing this. As you see, it's not that big change. I have a character as an array of characters, X, but this time I give it 15 possible units, as I already need only 12 plus the \0, which is not visible here. So in a way I add here some space because I want to exchange all the single pieces here by something. So far, all I print out here is nothing else as the hello world from before. You see, hello world. So I decided to exchange hello world to myCTalkthrough. And to do so, I took the all the single characters of myCTalkthrough, and for each character I created a value a decimal value, which is representing in ASCII or ASCII the letter. Here, for example, the decimal number 109 is nothing else but an M. If you interpreted it as an ASCII character. Binary, in the binary form, it is a 011011101. The same I did for Y, uppercase C, uppercase T, A, and so on. So that leaves me with a bunch of zeros and ones. And what I want to do now is I want to access exactly that spot where hello world is stored with pointers only, but in a very unusual way. And I will do that by interpreting these numbers with different types. That sounds kind of complicated, but you will see what it leads to. If I look at the M, somewhere in my computer's memory must be this here. And if you remember, digital binary numbers, bits are just interpreted always from right to left. So this sequence here of 8-bit means 1 byte is nothing else as an M. In my memory, it is not M, Y, C or uppercase C, uppercase T, A, L and so on. It is going from the right to the left. So the next 1, 2, 3, 4, 5, 6, 7, 8 bit are an Y. This is an uppercase C. This is an uppercase T. All these 4 bytes are an integer, because all integers we have already seen are 4 byte, have a width of 4 byte, and that are nothing else but 32-bit. So this 32-bit of these 4 characters, M, Y, uppercase C, uppercase T, I can also interpret it as a decimal number again. And that I did again with this and this and this and the T. And of course I did it here again. Here only I show you the last one. So what I had left over then was the G and the H. And that is, I know already, the decimal number 103 and 104. But in this case, I put them in a type of only 1 byte. And that is typically a character. So, what is all that good for? I will create myself some data types. And I create an unsigned integer pointer that I call ptr_int, and I want to point that to the value where x is stored. And now I create also a pointer to a character, and I let that also point so far just to the beginning of our string, to our x, to the spot where x stands. So what I now do is I create myself some values of these types. In this case, I create an unsigned int or I create 3 unsigned ints. I call them left, middle, and right. Here, left, middle. Oh, this, yeah, it's left, middle, right. It's not really right, or left, middle, right of the string. But here interpreted, they are exactly the other way around. They begin with the right. So don't be confused that this is on the right, but it's called left, because it is left part of my string, of my intended string here. This is the left part, myCT, and that I call unsigned int left and give it this value, which will be then written in my 32-bit 4-byte integer, which I call left. So, and then I have middle and I have right, and then I create also a character rest to the right, and that is the 103. Now I will start with assigning pointers. So, first of all, I create a pointer int, and to that I assign the value left. But this pointer here is dereferencing. So exactly where pointer actually points to, this pointer. So the beginning of hello world, exactly there, I write with the width of an integer a bit pattern, which can also be interpreted as this number. Oh, that's hard. So I override not only the age, I override HELL. So I override hell, you can say so, with this value, which is nothing else but these values, which put together again as myCT. So far, I hope you understood that. What I do then is, I move my pointer forward. I move my pointer forward one width of an integer. And then I do the same thing again. But this time, I write to the spot where the pointer now points to as a value, this value. And this value is a representation of this bit pattern. The same I do, of course, a third time, which gives me this here. So there are only a G and an H left, which I also need to write now into my array. But they have only half the size. I don't want to get out of scope of my 15 possible spots here. So I don't want to override 2 bytes. So for that, I choose a 1 byte stuff only. But actually, my pointer for the characters is also pointing at the H at the beginning of the string, which is probably not an H anymore. But anyway, I need to move it forward now. And of course, I could now 12 times move it forward with ++, but instead I use here also some totally legit pointer arithmetic with the pointer to char, which actually points to the beginning of the array, is now pointing to the end of the array. Even 1 over it, pointing exactly to where the \0 stands. And at that spot, I will write I will write the new value 103. Afterwards I move one forward. I need to move my pointer one forward. Rest to the right is my pointer here. It's my character, sorry. And that I want to raise by 1. Has that something to do with pointer arithmetic? No, it has not. I just raised the value here because by chance G and H are sequential letters and their decimal values are 103 and 104. So instead of assigning a new value, I just raise the value from 103 to 104. And then I move my pointer forward, and after moving the pointer forward, I write the value at that spot. That is meanwhile 104 because I raised it here. So I wrote 3 times big chunks of 32-bit and then 2 small chunks of 103 and or 2 8-bit, so 1 byte chunks, and that leaves me with an value up to 14 different characters in my new string. But to finish this string properly, at the last spot, 0 to 14, 14 is the last spot of that 15 altogether characters. There I now manually just write \0. That is nothing else but a termination. Now let's check out if it worked, but to give proof that it worked, I just print out X again. X is in the beginning hello world. What is it after my memory manipulation here? We will see. So here we go. Segmentation fault. Somewhere I did something wrong. Yeah, usually a segmentation fault is nothing else but a clear indicator that you tried to access some memory where you have not to access the memory. So we have to have a look here what is going on. Maybe it is something that somewhere I made a mistake with the pointer arithmetic, but as I see, I don't think so. So what else could have happened? I could have assigned a wrong value to a pointer where I wanted to assign a value to a pointer spot where the pointer points to. And that is here on line 47 the case. Here I assign to the pointer the value 103, rest to the right. But the value is 103, so I let the pointer to the char point in memory to some value 103. That is not what I was intended to do. So what I have to do here, I have to point to the spot. I have to dereference the pointer. And there I want to write the value to. So another try, we let the run, and as you see, I turned hello world to myCTalkthrough in a more than complicated way using pointers and pointer arithmetic. Yeah, for what of all things was this all good for? Yeah, the short answer is just because. The better answer is that it shows how you can make use of pointers to manipulate memory directly, and that for C, and hence for your computer, the meaning of any arrangement of zeros and ones depends on interpretation. Many people think that programming is about complex calculations or weird algorithm, but that's not true. It is all about types. And pointers are a tool to access and interpret values as of any type because they represent something like an extension to a type. They are a tool to throw off the earthly bonds and look into the face of an entity of higher consciousness and obtain a big piece of the cake of transcendence. My advice is to embrace pointers in the C programming language.